Good evening. My name is Dr. Eric Veary. I am a professor in the Department of Neurosciences here at the University of California, San Diego. And far more fun for me is I'm also the Associate Director of the Arthur C. Clarke Center for Human Imagination. And it's my great pleasure to have you here this evening for so many good reasons, but the best part is that I like to get to talk about Arthur C. Clarke, and so to take the podium to do so. So the Arthur C. Clarke Center for Human Imagination was established 5 years ago here at the University of California from the Arthur C. Clarke Foundation. Our mandate is to study and understand and make use of human imagination. And so we are a center across the campus with professors from cosmology and visual arts and science fiction and even a few brain scientists to understand what's happening in the human mind with the acts of imagination. We are what's called organizational research unit, and so that makes us quite flexible, but also makes us dependent on our fantastic sponsors and our government grants and corporate contributions for our research efforts. As I mentioned, we have cross-cutting research and activities across the campus in all kinds of laboratories, from exciting things like a collaborator of ours who was part of the discovery of exoplanets in the TRAPPIST-1 universe, to the fantastic art installations of our center director, Dr. Sheldon Brown. Sheldon. The other fun part of the Arthur C. Clarke Center for Human Imagination is our outreach. And we have had all kinds of different activities, including our science fiction film festival, and perhaps one of the most exciting ones that will be starting shortly, which is the Clarion Science Fiction Writers Workshop. I was very pleased to convey to our guest speaker this evening that UC San Diego, you may not know, has the highest number of awarded science fiction writers of any university in the world. And a few of them are in the audience tonight. So with our Clarion Science Fiction Writers Workshop, we bring young science fiction writers in who go through an intensive 6-week program of instruction and writing critiques and reviews, and many of them have gone on over the 4 decades, the last of which has been here at UCSD, to write winning screenplays and novels and short stories. So it's a super fantastic part of our Clarke Center to host science fiction. Which brings me, of course, to Arthur C. Clarke. And as I say, I just love to talk about him. I had the great fortune of meeting Sir Arthur personally at his home in Sri Lanka 15 years ago. And so audience participation time, who can say in the audience that Arthur C. Clarke changed their life, that they read his stories, were inspired by them? Now the hands are going up. There they go, Arthur C. Clarke, including our distinguished guest speaker who told me of his own reading of Sir Arthur, including his fantastic short stories. The one you may well know is called The Sentinel, which is what the science fiction movie 2001: A Space Odyssey was based on. Interestingly, The Sentinel will have its 50th anniversary next year, and watch out for Arthur C. Clarke Center special events around the 50th anniversary of 2001. Also, yes, exactly, yay, for sure. Even more notably is this year is the 100th anniversary of Sir Arthur's birth. And we have all kinds of activities, especially coming up in the fall. His birthday is December 16th, where we'll be participating in a science fiction film festival, giving the Arthur C. Clarke Center for Human Imagination Award, Film Award, and all kinds of other events that we'll have coming up through the fall. So please go to imagination at ucsd.edu, where you'll be able to see the announcements and links to many of the activities that we have. And so, imagination.ucsd.edu. Thank you for the correction. And so it's my great pleasure to have my co-director of the Clarke Center, Dr. Brian Keating in the Department of Physics here, to introduce our guest speaker.
Thank you very much. It's a great pleasure to be here. There's some seats in the front. Just don't take mine. Please, or give me a good tip and I'll give it to you. Sell my seat to you. So it's a great privilege. I am the token physicist here to introduce our esteemed guest speaker tonight, Sir Roger Penrose, who's the emeritus professor at the Mathematical Institute of the University of Oxford. He's won many awards and he's known for many, many things. I first encountered him at such an early age in high school that I was completely baffled by his work, which I have here. One of my favorite books of all time. I'm hoping to finish it someday. If you don't know, they sell Roger's books by the pound, okay? He makes a lot of money off these behemoths, and they're wonderful. I was remarking today on how exquisite it is that he combines the two kind of hemispheres of the brain that we're known for on the Arthur C. Clarke Center for Human Imagination, arts and sciences, beautifully together, where he synthesizes the works of art and as well as new directions in science, ranging from mathematical physics, pure math, to cosmology, to quantum physics. And although he's an emeritus professor, he is still actively engaged with research. And in fact, he's spearheading whole new directions in the study of consciousness, which is actually what brings him here in combination with this event that we're doing tonight. He's had tremendous influence, in addition to the work that he's done as an amateur. In my opinion, he's a professional level artist, but he inspired the works of M.C. Escher, or I guess you might say Esker, but his works on so-called Penrose tiling is just one of the many areas where you can see this influence that then extended to these beautiful pictures that I'm sure you've seen on your dorm room walls or your kids' dorm room walls with angels and demons interlocking in beautiful ways. That was deeply inspired by the work of Sir Roger Penrose. I want to just quickly read a list of things that he does and he's known for. So the first thing is that he invented Twister. You guys ever play Twister? No, he didn't do that. He invented twist-star theory. He'd be far richer if he did. He invented the notion of spin networks, geometry, wild curvature hypothesis, Penrose inequalities. As I said, Penrose tiling, which you can put on your Penrose stairs, which he also invented, and the Penrose graphical notation. So many things, singularities of space and time relevant to black holes, deeply influenced and collaborated and still collaborates with cosmologists ranging from Dennis Sciama, who was an advisor to him many years ago. He's passed away, and Stephen Hawking, famously. And I think there was a cameo of you in the Theory of Everything, I believe. Not with you, but someone pretending to be you. And maybe we'll hear a little bit more about that tonight. So I think I'm going to introduce Sir Roger. Afterwards, we're going to have a conversation, I believe, the two of us, maybe field a couple of questions, and hopefully it'll be a really enjoyable evening. So please join me in welcoming the fantastic, incomparable Sir Roger Penrose.
Yeah, that's working. Thank you. Back up, yes.
I'll let you back. I'm sorry.
I'm not very good at it either, so. No. See, I'm really good at it. What did I just do? There are too many knobs on these things. That seems right. Yes, I can probably do the rest of it. I mustn't press. What is that? Mustn't press. It's okay, as long as I'm up here somewhere. Yes, I'm sorry about that. This is the title of my recent book with the Princeton University Press. It's part of the title of this talk. I should explain something about the title because I think the Princeton University Press, it was in the early, I think something like 2005. I was supposed to give these lectures, and I think they woke me up too early in the morning or something like that and wanted a title for the series of talks that they wanted me to give, 3 talks, and I gave them this talk, this title here, and it was a bit rash because most of I think the 3 topics, at least 2 of them, the world experts were actually in Princeton, and it was a bit rash of me to talk in this way. I think they didn't come to my lectures, so that was all right. But anyway, let me start with the fashion. That had to do with, well, let me first say, let's get this going. If I press the right button, that's the right button. one of the ideas of string theory, which people say are its great merit, is that it's a very beautiful theory, or the mathematics is very beautiful. And I should emphasize that the idea of beauty in scientific research goes way back. So in the Platonic days of Plato, there were these, perhaps a little before Plato, there were these 4 elements, and the 4 known regular solids were supposed to be represent the elements. So we had the tetrahedron, the first one there, which was fire, and then we had the octahedron, which was air, and then the icosahedron, which was water, and earth was the cube. And as far as I know, it's not just, well, I should say it illustrates one thing, is when somebody discovered another one, there were 5, you see, you could always mold the physics into agreeing with the theory. So they had to think of another element, which was the ether, or whatever made up the cosmos, which seemed to behave a bit differently from what went on the Earth. So that was all right. You could have another element. But so you can modify your theory. If the theory produces something which wasn't part of the observations, you just modify your ideas and fit the other one in. The only thing I know that this is good for, apart from being nice and elegant, is that if you take a cube, take 2 cubes, and those represent 2 sticks, 2 solid things, that's the cube, and then you cut them up and you can make 2 tetrahedron, that's right, fire. So you can take 2 sticks, rub them together, and you make fire, and you get an octahedron as well, and that's the smoke. So you could produce fire and smoke out of 2 cubes. Anyway, it's the only thing I know which you can actually use this theory for, but never mind. It just shows that the idea of elegance doesn't tell you everything. It can be an important ingredient, but it's not everything. Okay, let me move onwards. If I press the right button, I hope I pressed the right one this time. Here we go. Now, string theory certainly had its origins in a very elegant idea. I should explain what these pictures are. These are meant to be Feynman diagrams. And, well, if you're a particle physicist, time goes this way, from left to right. But if you're a relativist like me, time goes upwards. It doesn't make much difference, but then you'll see that time is going upwards in this picture. And what the first one represents 2 particles coming together, making a third, and then that's splitting into 2 others. And here you have 2 particles and what's called exchanging a particle and so on. Now, these are different basic processes that particles can indulge in. But each of these diagrams represents a specific mathematical expression. And that's fine. It works beautifully well. The only slight problem is that this is meant to be quantum theory or quantum field theory. The only slight problem is when you have diagrams like this, which have closed loops, and it's the great strength as you can talk about these things, that when you actually strictly use the rules for what these diagrams represent, you get infinity. Infinity isn't much use, but they have all sorts of tricks for getting rid of infinities, and that's part of the theory. It's full of these tricks for getting rid of infinities. But it was suggested, I think Nambu was the main person who made this suggestion, that if you imagine instead of these particles, see if we go back and think about the Feynman diagrams, you can think of the particle in as its history in time would be represented by a line. So that's the particle starts moving in some way, and then it does something with some other particles, creates some others, or annihilates them, or so on. But then you have a problem because you get these infinities, and this comes about basically from the fact that you've got, well, you might say it's because you've got corners and things. Sorry, I got the wrong way. And this idea of the string theory is now, you might, instead of having the particle being a point, and so its history is a line, the particle here, I've done it wrong. The particle here is a loop. And so its history is a little pipe. And, oh dear, where is the thing I pressed to make the light go on? Oh, here we go. That's right. So you think of these pipes. So it's a sort of plumbing, if you like. These pipes join together in various ways, and it gives you a kind of unity between all these diagrams because you can just stretch them and squash them, and they seem to be the same diagram. And then you have these things here, these things represent what are called Riemann surfaces. It's a very beautiful piece of mathematics, and that was one of the appeals of this scheme. It relates to a very beautiful piece of mathematics, and because of these things are nice, smooth pictures now, the claim is that you actually get rid of your infinities, and that's one of the great strengths. So when I was first introduced to this idea by Leonard Susskind, I think it was, and I thought it was a wonderful idea. And indeed, I think it is an amazing idea with lots of potential. The only trouble was that it only worked. They discovered that it only worked when the number of space dimensions was 25. And to me, that was more or less the end of it. But I'll say a little bit more about that because it wasn't the end of it for many people. Let me go on. You see, what do you do with all those extra dimensions? Well, the idea was this, that the x, you see, we've only three dimensions of space instead of 25. And so it's 4 dimensions of space-time and 26, the idea was altogether. So you have 22 dimensions extra, and where are they? Well, the idea is they're sort of tied up in a little knot, which is so small that it doesn't bother you. And the picture is more or less here. This is the analogy of a hose pipe, and the hose pipe, dear, I'm really not good at this. I've got to press exactly the right spot. My thumb doesn't do that. Here we are. There's the hose pipe. So if you're a long way away from the hose pipe, it looks one-dimensional because it's just, it's one-dimensional. But if you get up close and you look at the surface of the hose pipe, you see it's got a 2-dimensional surface. And that extra dimension is small in the sense of it's wrapped up into something small. And so the idea is that on the macroscopic scale, on a large scale, it looks one-dimensional, but really it's got extra dimensions. And the idea is that what you look at on the large scale is the 4 dimensions of space-time, but when you look at it carefully, you see a lot of extra dimensions which are wrapped up in this little small thing. And that you're supposed to get away with it for that reason. Now, I had some problems with this because, well, I'll tell you the basic problem I had by relating this to something else which is useful for this talk. I want to say something, first of all, forget about the strings and everything. I just want to say something about big numbers. Well, ordinary arithmetic, first of all. When you multiply numbers together, you see, let's take a to the b. What does that mean? It means a times a times a times a, where the b, a's all together. That's a to the b. Now, you can do something a little bit more exotic by, say, a to the b to the c. Now, of course, you could read that 2 ways. You could be a to the b to the c, or a to the b to the c. Well, if it was just a to the b to the c, that wouldn't do you any good because then you can write it as a to the bc. So it's a to the b to the c is what it really means. So that means if you have a times a times a that many times, how many times is it? Well, it's b times b times b, b times b times where it's c of them. So that's what it is. Now, we have this sort of thing here. This is, if you just want to have 10 to the 100. Now, why am I saying 10 to the 100? Well, this is what's called a googol. And there was a mathematician's nephew, I think, who, I forget his name now, who liked to have big numbers. He was quite young, about 10 or so, and suggested that here was a really big number. Put down 100 zeros, like that. I should say that this number does feature in the book, because it's, roughly speaking, the number of years that it takes for a black hole finally to evaporate away according to Stephen Hawking's process, Hawking evaporation. So a googol years is about the length of time that the biggest of the black holes will live for. And that's, so okay, so that's a useful number to know, maybe. But here, you see, then this nephew decides that wasn't big enough, and he wanted a bigger number. So he and his uncle decided eventually that, well, a good thing would be a thing that they called a Googolplex, where the number of zeros was a googol. So you take a googol zeros, and this is 10 to the 10 to the 100. Now that number is not all that big. I saw Ron Graham a minute ago, and he knows of numbers which are absolutely stupendously larger than this, but let's not worry about this. For an ordinary person, that's a pretty big number. It does feature, it's pretty small by comparison with something I want to say, which is actually the improbability of the universe in a certain sense. So let me come to that in a minute. You see, the point I really want to make here is if you have double exponents, a to the b to the c, c is all important, and it doesn't matter what a is, more or less. And the thing I've got here as an example, this is the, if you like, the specialness of the Big Bang. I want to say that the Big Bang, as we see it, is a very, very special one. And how special is it? Well, it's roughly speaking 1 part in 10 to the power 10. I think I've got 10 to the power 10 to the 124. Now, one thing I want to illustrate is that it doesn't really much matter whether that 10 is 10 or E or 2. If it's 2, you see the number at the top hardly changes at all. So it doesn't matter what the bottom number is much, but the top number is all important. Okay, that's the main message I want to give you, except to say that this improbability of the universe is, in terms of googol's, I've forgotten this, googol multiplied by itself 1,000,000 times or something like that. It's easy to see from here, but let me not say it because I can't see what I've written very well, so let me go on. Okay, now I want to let these numbers become infinite. And some of you may know about Cantor's theory of the infinite. I'm just showing you this picture to say you what it's not, because this is one of the things about Cantor's infinite. You can take the number of natural numbers, 0, 1, 2, 3, 4, and that's the smallest of the infinite numbers. And one of the things that Cantor's theory says, if you have pairs of natural numbers, that's no bigger than the number of natural numbers. And you can see the pairs of them are represented by this array here, going off to infinity in both directions. And I have these vertices of this lattice give you the pairs of natural numbers. Those are the coordinates. And the thing is, you can count them by going backwards and forwards like this in this zigzag fashion. And you can exhaust the whole lot just by counting individual numbers. So this is Cantor's argument for showing that there are no more pairs of natural numbers than there are individual numbers. But you see, this kind of counting is not very continuous, because you can see if you want to go from this pair to this one right up at the corner, you have to go all the way down there and all the way back again. And when they get really big, you have to go a long way. And so the close numbers in the pairs, or close numbers in a number that you're numbering the pairs here, and that's what I just say. You count along this zigzag thing. The numbers can be far away even when the pairs are close to each other. So it's not very continuous in this sense. So what I want to say is something counting infinite numbers, but where it's really continuous numbers, and you want to make sure that it really is continuous. So this is the idea, and let's say what I'm talking about here, where you see, first of all, as opposed to the plane in the discrete case being no more than in the straight line, in this continuous counting, the plane has more numbers in it than the line, and the solid would have more numbers again. So I'm going to call it infinity, or infinity to the 1 is the number of numbers in a line, or number of points in a line, continuous points in the line. A to the b, a squared, a to the 2 is the number of points in a plane or a curved surface, and a to the 3 is the number of points in a solid, and a to the n is in an n-dimensional space. You can make sense of all this. I don't want to say it's just waving of the hands. It really does make mathematical sense. But you can talk about these infinite numbers, and again, you find that the top exponent is the all-important one. And that has a role to play in what I want to say about string theory, so I'll come back to that. But first of all, let's just say what I mean here. You see, suppose I now count the number of functions. And this first picture here is supposed to be discrete functions. So when I say function, you can think of each point at the bottom can take all the possible values upwards. And if these are discrete, and if it's A upwards, I think, and B this way, then the number of different graphs you could have is A to the B. That's just ordinary discrete things. But what I want to say, suppose it's continuous curves now, then I would write that, you see, the number going up this way, it's just a line as I've drawn it, but it might be a high-dimensional space. So the number here, number of different graphs here would be A to the B to the C, and so on. So let me show you an illustration of this, which is, if I can make this thing work. So suppose you have magnetic fields, or electric fields, say, in 3 space. And how many electric fields are there in 3-dimensional space? Well, at each point, you have the electric vector. So that little arrow there is supposed to represent the electric vector. And you need 3 numbers to describe that vector. It has 3 components. And then I have the 3-dimensional space. So what is the number of different electric fields? Well, it's infinity to the 3 to the infinity here, that's the line which I'm supposed to be indicating. Bottom line, that's right. So infinity to the 3, infinity to the 3, infinity to the 3. Now you see, it's the top 3. The trouble is these 3's represent two things. It's the top one is the dimension of the space. And what I want to say is that if you have infinity to the A to the, infinity to the A, infinity to the B, to the, there's a C at the top, to the infinity to the C. The C is the all-important one. And it doesn't matter much what the other ones are. So that's the point I want to make. And that's the dimension of the space. So it's the top 3 here, which is all important. Now, why am I saying all this? I'm saying all this because if you have a space which has more dimensions than 3, then the number of functions in that space is huge, absolutely huge, by comparison with the number of components. So you see, you might have a field which had a certain number of components, but if it's in a large number of dimensions, it doesn't matter a hoot what the number of components is, it's the dimension of the space which dominates everything. So this was a reason why I didn't like the idea of more dimensions of space than we seem to see, because that means that the functions in that space, if it has more dimensions, will completely swamp what we see. And so why don't we have all these degrees of freedom completely swamping everything, flooding the whole space? And that would ruin the whole of physics. Now, the sort of argument that people made here, and let me go ahead. Well, here's the point. I should have given this slide here. You see, infinity to the A is larger than infinity to the B. Or infinity to the A, I can't read what I've said, but you can read what it says there. If the B is bigger than the D, then it doesn't matter what A and C are. So it's the top exponent which is the important one. And that's the dimension of the space. And it doesn't matter a hoot how many parameters there are, how many degrees of freedom you're talking about. If the space dimension is larger, it's going to swamp everything. So that was the point I was making. But then people said, well, there's a history to this, because there was a wonderful theory put forward by Kaluza, who was, well, whether he was German or Polish depends on, he was born in a country, in a place which is now part of, I forget which way around it was. It was part of Germany, is now part of Poland, or the other way around. But anyway, you can take your pick. But he proposed this wonderful idea. Einstein had recently introduced his idea of space-time, in which you had a curved space-time, I should say, in which the gravitational field was encapsulated in the curvature of this space-time. And the idea was, could you do something better than that? Because you don't want just gravity, you'd like to have electromagnetism. And Kaluza had this wonderful idea that if you introduce an extra dimension, so that the space-time is 5-dimensional, then you could incorporate electromagnetism and couples with gravity in exactly the right way. So that was really remarkable. So people say, well, 5 dimensions is good, why not higher than dimensions? But there's a key point here, and that is that in Kaluza's theory, you needed to have a symmetry. So, I pressed the wrong button again. I'm going to do that, I'm afraid. You need to have a symmetry, which is, you see, here is space-time as we know it, so it's 4-dimensional. And then we have these little curves sitting over each point. You imagine another curve. So the whole thing is 5-dimensional. But because these curves have a symmetry, you can rotate it around in that extra dimension. That's not really an extra dimension. It's an extra dimension which doesn't carry any more information. So it's all right to have an extra dimension, because all the functions on your space are down here, not up there. So that's fine. Klein changed the idea a little bit by making these extra dimensions small in the way that string theory does. And I don't know whether he was allowing you to have extra freedom in those dimensions or not. It's an example of what's a bundle. I don't think I should talk about this. It'll take too much time. But it's an example of what's called a fiber bundle. And you want to say that the freedom is in the bottom, not in the fibers. As long as you have a symmetry. Well, people used to say to me when I complained, they say, well, why don't you see all these extra dimensions? How do you keep them hidden? And the argument was as follows. Well, you can't excite those extra dimensions because it would take too much energy. The amount of energy it would take to excite the smallest mode of excitement of those extra degrees of freedom would be something like the energy in an artillery shell. And you've got to, they imagine you say you're doing this in a particle accelerator, and that accelerator has to give that particle that much energy that if it was in this room, it would be a disaster for us, I'm afraid. But so that was what's called the Planck energy, and that, well, it's actually not quite that energy, but never mind about that energy, which would be ridiculously large, so the argument goes. Well, it would be ridiculous. I mean, the point for me is that that's ridiculously large for an accelerator, yes. But that exciting that extra dimension is for the entire universe. So that amount of energy, an artillery shell, for the entire universe is utter chicken feed. And you consider you might imagine here, this is my picture, where we've got the Earth in its orbit around the sun, and the amount of energy in the Earth's orbit around the sun is million, I forget how many millions it is, more than the energy you need to excite that extra dimension. So if that energy is spread out over the Earth's orbit, per se, it's a ridiculously tiny change to this. And so there's no reason whatsoever, as far as I can see, why you couldn't excite that extra dimension, and it would get excited. And it would also be a disaster because you can use singularity theorems that Stephen Hawking and I proved to show that that it would not just excite that, it would be a catastrophic collapse in the extra dimensions, and so the whole thing would go to pieces. Well, anyway, that was my argument against all this, and I actually gave this argument in a conference just a little bit before I started lecturing in Princeton. I think it was a year before, and it was one of Stephen Hawking's birthdays at the conference. I was somewhere else first, and it was only the last talk of the conference. And I was a little bit worried that by giving this talk I might be tarred and feathered, because there were lots of experts in string theory in the audience. And although I escaped with being tarred and feathered, the next day there was a meeting for a sort of more popular conference. And I was wondering, well, what people would worry about my arguments. And Gabriele Veneziano, who is one of the originators of the ideas of string theory, came up to me and complained about something. He said, what about this? I said, oh, no, I didn't mean that. He said, oh, I see. So he said, I like him a lot. He's a very nice fellow. And then Michael Green came up, and he said, well, look, what's wrong? You haven't taken, no. And then Gabrielle said to him, no, he didn't mean that. He meant this. And they started arguing with each other, so I snuck off and let them argue. It was an interesting day, because I sat down for lunch afterwards, and I was sitting down at this table, and Lenny Susskind came and sat down opposite me. He was the one who initially inspired me to think about string theory as a nice idea. And he sat down, and I'm trying to get the wording right. It was something like this, pretty well word for word. You're completely right, of course, but totally misguided. And I was never quite sure what he meant, but I think it was something like, don't worry about detailed mathematics, we know what we're doing, and forget it. But I don't know if that's what he meant, but it was a curious comment, I thought. But anyway, it's very curious that I gave this lecture. It was written up, no complaints of any kind, no suggestion that the argument was wrong, no suggestion of anything else about it, no saying, oh dear, yes, that's a problem. Absolute silence. And then also this has been true with this book. I haven't had anybody complain about my argument it's in the lectures at Princeton. Nobody complained about it. And I haven't yet have maybe there's a string theorist in the audience who wants to complain to me about the argument. But it would be interesting. I'd like to have complaints, actually, because otherwise I have no idea what people think about it. But I can't see what's wrong with the argument myself. Anyway, let's move on. This talk is supposed to be not just complaints about current ideas, and that was a complaining about string theory a bit, or at least the extra dimensions of string theory. And actually, after my talk, which was on the fashion, the first talk in Princeton, a worried student came after me and said, what should I do? He was thinking of working on string theory, and he was a little bit discouraged by what I was saying. And he's saying, was there anything else he thought I might work on? Well, I didn't say twistor theory, which is what this is a picture of. which is what I was working on, partly because it's a bit too mathematical, and I wasn't sure that... Well, it has also a problem which is still not totally resolved, and perhaps I... Well, let me say, in my book, I do have a little section on this stuff. So this is the picture from it. In fact, all the pictures I'll show you are from the book. This is a picture of twistor theory, roughly speaking. And so just to tell you what it is, I'm not telling you what you used it for or anything here, but it's a nice mathematical picture. Of course, that doesn't mean it's useful in physics, as I've emphasized before. But the picture on the left is meant to be space-time. So you can think of this as a four-dimensional picture. Of course, I'm not drawing all the dimensions. And here's a point down here in space-time, or that's what we call an event. And this is the light cone of that event. That's all the light rays, which you see a light ray. Here's a light ray up there. You think of a particle moving along with the speed of light. So it will be a straight line in this picture, and the way you draw it is the speed of light as though it was 1 in the picture, so that the thing is at 45 degrees represents light ray. And what twistor theory does for you is the following. The light ray is to be represented by a single point in a new space, and the point over here, you think of all the light rays through that, and so this is this, you see, each light, suppose you're sitting at that point, you look out at the sky, all the photons coming at you from all directions is the celestial sphere, and that celestial sphere has nice mathematical properties. It behaves like a complex one-dimensional space. I won't go into all this because it would take me too long. I just want to show you that there are things you can do using beautiful mathematics, and they seem to me to be much closer to the idea of physics because you have the right number of dimensions. That's what's, you see, I should say that when people used to ask me why I didn't like higher dimensions, I had two reasons for not liking it. One was the public reason, which was more or less the reason I've given you, that these extra dimensions, you can't really hide them. And how do you hide all those extra degrees of freedom? And that was a main argument. The secret reason was that twistor theory didn't work very well in that number of dimensions. And twistor theory is very specifically designed to be a 3-space and 1-time dimension. It really doesn't work properly with any other number of dimensions. You could start it, but it doesn't get very far. But it works beautifully if you've got 3 dimensions of space and 1 of time, and then these ideas of complex geometry work very beautifully. I won't go into this. There are problems with it, which I think we do know how to solve, but there's a lot of things we don't know how to do. Let me not say any more about that. Okay, what's this? Well, you see, I've talked about string theory, and one of the complaints that people have I haven't mentioned, but usually people who don't like string theory do mention, is that it doesn't make any predictions. And the usual argument is, oh, well, you need all these artillery shell accelerators giving you an energy of that much to a particle before you're going to test anything. So they don't mind it being not testable because it's way beyond the scope of particle accelerators. Well, what about the next thing, which is the faith? Faith, I should say, is about quantum mechanics. Now, it's completely different, utterly different, in the sense that whereas string theory has absolutely no predictions, which are testable, may have untestable predictions because they're way beyond the scope of what we can experiment with these days. But quantum mechanics has absolutely vast numbers of confirmations, predictions, and so on. So it's a completely different kettle of fish. It is beautifully confirmed. And one of the initial types of experiment that people talk about is the Two-Slit Experiment, very famous, where we have... oh yes, I still haven't mastered this. The button which I have to press is too tiny for my thumb. There we go. This is, suppose you have a couple of slits there and a screen behind, and this is, say, an electron gun. It's going to fire, oh, I'm no good at it, you can see. It fires electrons, or some other particle, say, through the, they could be photons, through the slits. Now, first of all, I'm going to close one of the, put a little cover on one of the slits, and it fires through the other. And you see what you get, this sort of scatter picture. The particles might get deflected as they go through the slit, but there is a sort of middle line, which is where the particles mainly hit, but a scatter on one side or the other, but a little bit of you can see the indication of where the slit is. If you close that slit and open the other one, you have a very similar pattern, but the pattern is moved over just a little bit because the slit's in a different place, but it looks just about the same. So what happens when you open both slits? You might expect that you get this picture plus that picture. Nothing of the sort. You get these bands where certain places where you find that the particle can't reach at all, other places where it's more likely to reach than the other two pictures added together. So P and Q. P is the example of where you, well, whichever it is. I can't see these things. I'm sorry about that. You can see them. So you get places where you get these bands of enhanced. I mean, that makes no sense. You see, if a particle behaves like a particle, why doesn't it just add the two pictures? Well, the thing is, this is the thing, it doesn't just behave like an ordinary classical particle, but it behaves, in a certain sense, like a wave. And the wave is what gives you the bands. So you see the particle behavior and the wave behavior both at once, because you get individual points on the screen, that's the particle behavior, and the wave behavior is the interference. So it's a very beautiful illustration of how quantum mechanics mixes these two ideas together. And you have particles behaving as waves and waves as particles and so on. Now I'm not going to say too much about the way we work quantum mechanics, but I will say something about it. You see, what's this about? Well, you see, according to quantum mechanics, it's not just true that individual particles could be two places at once. See, in order to explain the bands, you have to say the particle somehow feels out both slits. It doesn't just go through one slit or the other. It seems to go out through both slits at once. And it interferes with itself, and some of the roots cancel and others enhance each other. But the particle has to be considered that it goes through two at once. And that is the way you do quantum mechanics. Crazy, absolutely crazy, but it works. Now, this is an example, my humane version of Schrödinger's cat, you see. It's the cat going the two slits, you see. So you could say, why doesn't this work on a much bigger scale? So what am I doing here? This is the cat behaving like a particle going through two slits, sort of. And so what's the experiment here? Well, I've got up at the top here, did I press the right knob? Oh no, it's the wrong knob, sorry about that. Don't know why I'm so bad at this. Okay, you see here is what's called well, there's a laser which emits a single particle. And then here we have a mirror, well, you might think of it as a half-silvered mirror, or a beam splitter as it's called, that the photon goes through it and is reflected at the same time. So it shares its existence between those two roots. And there it is. You see, particles can be two places at the same time. But if it goes through one, it activates a detector which opens that door. So if it goes down, it opens the A door. If it goes horizontally, it opens the B door. So if you follow Schrödinger's equation has this behavior of being linear. And that means that if A does something or B does something, that the superposition of the two must be a superposition of the two. So that the doors must be, one door is open and the other door closed, superposed with the other door being open and the one door closed. It's a bit hard to draw all that, but this is if the photon goes one way, it opens one door, the other's left closed. If it goes the other way, it's the other way around. And the poor cat sitting here, it encounters this superposition. It wants to get the food, which is down there. You can see the food in the room. And so the cat wants to go through the door to get to its food. But since the doors are in a superposition of two places, the cat must be in the superposition. So it's a superposition of two doors. Well, Schrödinger's version was a little bit less humane than this one. But the idea is that Schrödinger was demonstrating, basically, that his equation tells you nonsense. His equation tells you that a cat could be dead and alive at the same time, or in this case, the cat could be going through both doors at once. And that's what his equation tells you. And so usually quantum mechanics, people say, well, no, you have to interpret it in some way, which means you've got to make a measurement or something. Well, why doesn't the cat itself make a measurement by noticing which door is open or something like that? So you have a little bit of a problem I've been struggling with this ever since when I went to Cambridge as a graduate student, I went to lots of lectures which weren't anything to do with what I was supposed to be doing. One of them was a brilliant lecture course by Bondi on general relativity, and that influenced me greatly. Another was a lecture on mathematical logic, which led me to Gödel's theorem and worrying about consciousness and things like that. And another lecture was a lecture by Dirac, the great quantum physicist, and his lecture was beautiful, completely different from Bondi's lectures. Was full of excitement and the waving of hands and all this sort of thing. And Bondi's was very precise and very elegantly done. And right at the beginning, he gave a demonstration illustrating the superposition principle. He said in quantum mechanics, see, a particle can be over here, or it can be over here, then it can be all these combinations have been here and here at the same time. And that's the superposition principle. And then he broke a piece of chalk and said, well, it's an illustration of this piece of chalk being in two places at once. And my mind wandered at that point. I don't know what I was thinking about. And then he had an explanation why the piece of chalk was not in the two places at once. And I came back and I thought, what did he say? And I've worried about that ever since. He said something, the word energy, I think, came in there somewhere, but I couldn't see what energy had to do with it. So I've been worrying about that ever since. And I'll give you some bit of my worries here, I think. I've forgotten what I have on these slides, but I think that's one of them. Well, you see here, what's this about? This is, I should explain the origin of this picture. I was asked by the Hans Christian Andersen Society to give a talk. They were just coming up to the 200th anniversary of Hans Christian Andersen, and for some reason they'd invited me to give a talk. And I was very puzzled by this because what have I got to do with Hans Christian Andersen? No, I don't have anything to do with fairy tales. Well, then I remembered, of course, that I'd written this book with the title The Emperor's New Mind, and this, of course, was a play on the Emperor's New Clothes, which was a famous Hans Christian Andersen story, which very much was influencing what I was talking about in the book. But I had to think of something else, so I thought of the Mermaid. You see, this is the Little Mermaid story. And in my lecture, I related it to quantum mechanics in various ways. Well, one of the ways was that the mermaid, towards the end of the story, she is I can't remember why, but the thing is, it's in the night. And when the sun comes up, the first ray of the sun, when it hits her, she dies. So I thought, well, why don't we save her by putting a mirror between that beam of first ray of the sun, and so it gets reflected up into the sky, and she's fine. But then, of course, well, you know what I'm going to do, make it into a beam splitter, or a half-silvered mirror, and so the photon is split between going one way and the other, so she's in the superposition of being dead and alive. She's a Schrodinger's mermaid. So that was one of the uses of the mermaid in that lecture I gave. But it doesn't feature in my book, I'm afraid, but it does feature here as an illustration of quantum mechanics. So this is an illustration of where quantum mechanics is done. So this is really what it's about. The bottom part of the picture represents the quantum evolution, the Schrödinger equation, if you like. U stands for unitary evolution, and this is the Schrödinger equation. It's a deterministic evolution of the quantum state. So it chugs away, and you could put it on a computer if you want to. It's rather hard to do, but you can put it on a computer. And that is the quantum world. What's at the top? Well, that's the classical world. And the letter C is being used here for classical world. And the quantum world, you see everything's all a bit of a mess and tangled up and unfamiliar creatures and who knows what's going on there, and it's a very unfamiliar looking world. But then we have a more familiar world at the top where things are separated and so on. And what's the mermaid doing? Well, she, of course, is partly in the quantum world and partly in the classical world. She's magical, too. So she represents how somehow the classical behavior comes out of the quantum world. And the way that occurs in quantum theory is by another process, which is called the collapse of the wave function or the reduction of the quantum state. That's R in the picture, where suddenly this great entangled mess of things you do what's called making a measurement or something, what it means is a little obscure, because when you make a measurement, you've got to use a piece of apparatus. And if the quantum world is everything, then that piece of apparatus, which does the measurement, must also be part of the quantum world. And so why isn't it at the bottom? Well, that's never explained. But there are all sorts of partial explanations which people give. I don't believe any of them. But something must happen. And I think something that happens is something mysterious like this mermaid, but not so mysterious as that it won't be part of a future physics. But it's not part of the physics that we have today, because the part of the physics we have today is either quantum or classical. If it's quantum, it belongs to this bottom world, and you get these superpositions of cats going different doors and so on. And if it's the top world, you get going only one door, not the other. And that's what you see up here. And how does that work? Well, how we do quantum mechanics is illustrated more in this picture. This is the graph. Well, I'm afraid I'm doing the particle physicist time going horizontally. And the quantum state is represented by upwards. So the quantum state evolves according to Schrödinger's equation, or U. And then somehow a measurement gets made. And one of a number of set of alternatives comes about. And then that evolves, and then one of them comes about, and then that evolves. That's the way we do quantum mechanics. It looks completely crazy, because there's not a systematic system to the whole thing, but that's the way we do quantum mechanics. You plug along with this unitary evolution, and then suddenly you change your mind, and you take it as representing a probabilistic set of alternatives, one of which takes place. Some theories say, well, they all take place, and you get all these many worlds happening all at once. But I want an explanation which describes the world we live in, and that's only one world. So you need something which really, this is an approximation to. It's crazy as a theory as it stands. It's the way we do quantum mechanics, but we want a new theory which really makes sense of it. So let me try and go ahead without making a mistake. Now this here is a quantum illustration of what I think gives a reason for a new theory, or at least a reason for what it might be. And I'm trying to explain, I don't think I can explain all of this here, but let me just show you. I like the picture because when I drew it, you see, I drew these pictures and they were sent to the man who looked at them and said whether it was good enough for the reproduction and so on. He was supposed to improve it, but I ended up by improving it myself because it was easier. But he thought it wasn't going to work very well because this picture at the top, you couldn't very well see the dials and all that, and it needed a little bit of clarity. What I had to explain to him is this is a completely fictional piece of apparatus. It doesn't mean a damn thing. So I just put it up there so you could imagine some complicated piece of apparatus. And the point is it uses gravity in it. Somehow the Earth's gravitational field is incorporated in the quantum system you're describing. And the point I'm making here is there are two ways you can consider the Earth's gravitational field. One is the ordinary way that most physicists would use, and they do what's called putting a term in the Hamiltonian to represent the gravitational potential. If you don't know what that means, it doesn't matter. But that's the standard way, and you can do that. But that's only Newtonian way. And we don't believe that the Newtonian way is the right way. We believe that the Einsteinian way is the right way. And the Einsteinian way is to regard the gravitational field as equivalent to an acceleration. So you imagine yourself falling in the gravitational field, and then your coordinates are this falling free field, and then you do it this way. And you find almost the same answer, whichever way you do it. But there's a technical point which I don't think I can explain. But the technical point is that the almost isn't exactly the same answer. It tells you it's fine if you've just got one gravitational field, but if you've got more than one gravitational field, you're in trouble. When I say you're in trouble, it means that you can't actually apply the quantum mechanics. You have to do something illegal according to the rules of quantum field theory. Let me not go into any detail there. But it points out that if you have gravity in the picture, you've got to think of something else. Quantum mechanics doesn't work if you incorporate it with the Einstein equivalence principle, or Galileo-Einstein equivalent principle, which says that a uniform gravitational field is equivalent to an acceleration. And that causes problems. And this is the picture illustrating the sort of problem you have. Here we have, at the bottom, a lump of material. I'm not having anything as complicated as a cat. It's a lump of a stone or a rock or something, which is put into a superposition of two locations. And then upwards we have now the picture of the space-time. Oh, I'm doing it wrong. Picture of the space-time, and these are the different accelerations you have, you see. And the fact that the black one gives you the black curves for the accelerations, and the gray one is the gray curves. And the fact that they differ means that if you're trying to do the free fall argument, you're in trouble with trying to make them match. And that, if you look at this carefully, you see it leads to a conclusion which I've illustrated here. This is a picture of what happens to the space-time. I'm afraid it's a little horrible looking picture, but never mind, that's the claim, that what happens is something like this. You have here, it's really the picture I had a minute ago with the two space-times, but the two superposed space-times have to come about because the rock gets moved into its superposition. And so initially the rock is in one place, and this is the curvature it introduces. And as time evolves, the rock moves into two positions superposed, and so you have two space-times which are superposed. And the thing is that this only lasts for a certain time, which you can estimate, but in terms of the energies involved in the displacement here. I won't go into the details there, but there is a well-defined formula which tells you how long it could last. And this, if there's a big displacement of mass down here, then it's a very short time. If there's a little displacement, it could be a long time. And it's such that the space-time displacement is of what we could say 1 in what are called natural units. That's where you put Planck's constant equal to 1, the speed of light equal to 1, and the gravitational constant equal to 1. You can just get away with doing all that. And if you do that, then 1 unit of time tells you how long it takes for this to take place. I wasn't saying anything about consciousness in my book, except a little bit when talking about this. But this does relate to the ideas which Stuart Hameroff and I have been trying to develop, what we call the ORC-OR theory, because it makes use of this idea where there is this choice that the universe seems to have to make. It does one thing or another, and that is the choice which is made in this time that you can estimate from this picture. And the idea is these choices are taking part, not just one displacement, but there could be lots and lots of mass scattered, well, not scattered is the wrong word, but in an organized way over the brain in these microtubules is the idea. And the amount of, you could calculate how much energy, how much mass there is displaced, and that gives you a time scale. And the idea is that a conscious experience comes about with this kind of choice that is made. So if there is a notion of free will, it's related to the choice that the universe seems to have to make whenever this measurement, or whatever it is, self-measurement takes place. Okay, well that's a little bit of speculation there, but we do have, the point about this is that it is experimentally testable. Well, I mean, what's experimentally testable, if you like, is the idea that I'm describing here and here, that this reduction takes place in the time suggested. And this is a cartoon of an experiment which was being worked on for, I don't know, about a decade and a half, or maybe 2 decades by now, primarily by Dick Baumeister, who, this is an idea that we developed together with some other people, that you have, say, there's a laser here emitting a single photon, and this gets split into 2 directions. And this one is kept in what's called a cavity, and it reflects backwards and forwards like this, probably about 1 million times. And this one has a funny kind of cavity where it reflects against a little tiny mirror here, which is a little cube, which is about 1/10 of the thickness of a human hair. And if it gets hit 1 million times by this photon, it will get displaced by something like the diameter of an atomic nucleus. But the idea is that that should be enough, if this scheme is right, within a period of seconds to minutes, depending on details, decay into being one or the other. So it's in a superposition of being hit by the photon, so it's displaced, and that's when the photon goes this way. If it goes the other way, it's not displaced. So that it's a superposition in one place and the other. And that superposition, the claim we make, is that it can only last for a certain length of time, and if it becomes one or the other in that length of time, you try to bring it back, and you see you've lost coherence, and this detector up here would see something. Whereas if it didn't lose coherence, it would go back into the laser and you wouldn't see it. So this would be a test for whether this is right or not. So it would be very interesting to see. There are other tests that have been suggested more recently for whether that will happen. Okay, cosmology. This is the fantasy. Now there's a little bit of a different story here, because I was really aiming the chapter on, the third chapter on inflationary cosmology, because the normal picture that we have today of cosmology is a bit like this thing here. Time is now going up the picture in the way I like, and so time is going up this way, and this represents the entire universe. Well, you might ask, what's all the frilly stuff at the back? Well, that is just because I don't want to prejudice the issue as to whether the universe is open or closed. It might go and do something at the back, or it might close up on itself. It doesn't matter much for what I want to say. It's easier to draw the picture if it's closed. Now, this is the history of the universe. Big Bang, it expands, slows down a bit, and then, oh dear, I'm really no good at this. Slows down a bit, and then it does this exponential expansion, which got the Nobel Prize recently. The universe seems to be doing this accelerated expansion. People refer to it as dark energy or something, but it seems to be consistent with the term that Einstein introduced into his theory of general relativity, initially in 1915, and then he introduced another term in 1917 for the wrong reason, because he wanted a static universe, and then he got worried because the universe was observed to be expanding, so he regarded it as his greatest blunder to introduce this term. But to say that this term was his greatest blunder was actually a blunder, because it actually seems to be true. So this is rather curious that Einstein introduced it for evidently the wrong reason, but it seems to be the right theory. Okay, so that's fine, explains this picture beautifully, but what have I left out? I seem to have left out a major part of the theory, which is what's called inflation. So they're supposed to be tucked. Well, you see, should say, oh dear, I'm really bad at it. Sorry. It's tucked into that little black point there. So inflation might be in the picture, you wouldn't tell, because on the scale of this picture, it's pretty well to scale, but the scale of this picture, it would be tucked into that little black spot at the beginning. But the other reason it's not there is because I don't believe it. Well, I don't believe it. Originally, I didn't believe it because it looked very artificial. And this is the picture, one of the reasons I feel it's artificial. Because, well, the main thing that inflation depends upon, at least the modern version, a thing called the inflaton field, which is a completely made-up field. And it's got a potential function, which is represented in these different graphs. You have to draw the graph by hand, basically, so that it does what you want. And this is just a sample of different graphs of what the inflaton field is supposed to do. And it shows you that nobody has a very clear idea, except that it's got to have a general picture like this to do what you want it to do. But it's a made-up field, and there's no reason from particle physics to believe that that field is there. But it's supposed to do various things which I didn't believe it did. One of them it was supposed to do is to iron out the universe, because the universe is very uniform. The early universe is very, very uniform. And inflation was supposed to make it smooth. Now, the pictures I've got here are various models of the universe, not necessarily with inflation in them, but this is, oh dear, I need a lesson on how to work these machines. Here we have the Big Bang. Sort of, if the universe was closed, it would look something like this, with it expanding out, and then it might collapse again and produce a great mess. But the great mess isn't anything like the Big Bang. So this is a very general kind of singularity you get when it collapses, and this is what we have. Now, just reverse the time, and this is telling you why, if you have inflation, it doesn't iron out this great mess. The great mess will be inflation or no inflation. You can see from this general argument that it won't iron it out. Okay, well, I shouldn't have wasted so much time on this, but let me go on. Now, you see, there's another argument which worried me for a long time, which has to do with this thing called entropy. See, entropy is a very fundamental part of physics. It tells you a measure, if you like, of disorder. So the second law of thermodynamics is more or less a statement that the entropy increases with time, or the disorder increases with time, if you like, or it gets more and more random as time goes on. The top picture is a nice illustration showing you the sort of thing that happens if you have a gas in a box. You might have it cornered, blocked off in the corner, you release it and it spreads out over the box. Now, the universe that we see, there's a problem, because if the second law of thermodynamics works way back in time to the Big Bang, where you see it's telling you that as you go into the future, the entropy goes up, the randomness goes up. So that means if you go into the past, the randomness goes down. So it must be very low entropy in the early universe. Now what we see, that was the main evidence for the existence of the Big Bang, is this cosmic microwave background. And the cosmic microwave background is this wonderful spectrum. I don't think I've got this picture here. The cosmic microwave background, one of the main features, is it's got this curve, if you look at it, which, let me not explain it. It looks like this famous Planck curve. And the point is, it tells you that what you're looking at is maximum entropy. Now, maximum entropy, you might say, that's ridiculous, because it should be minimum entropy. As you go back and back and back in time, it shouldn't be a maximum, because it's gone down and down and down. So why is it a maximum? Well, what you see seems to be a maximum. Well, the universe is expanding, so you might worry about that, but that's not the answer. It's clear, you can give good reasons why it's not the answer. Let's not go into that, though. But the point is that what you're seeing is radiation from matter and radiation basically in equilibrium together. So that is what's called a thermal state. That's a maximum entropy state of matter and radiation. And that's what you see is radiation from that. What you're not seeing in that is the effects of gravity. However, there is another feature of the cosmic microwave background, and that is that the universe was extraordinarily uniform in the early days. Well, you see, that would be consistent with the top picture if it's high entropy, but you want low entropy. So the matter here in this picture doesn't do what you want. But if you imagine a box, galactic scale box, say, where at least there's just stars running around, then the tendency would be for them to clump because of gravity and eventually produce black hole. Now you see, that goes in the opposite direction. So what you're seeing is great uniformity over the sky. In other words, you're seeing a combination of this and this. Low entropy in gravity, high entropy in everything else. Now this seems to me to be an extraordinary puzzle. And I never understand why cosmologists don't list as the big puzzles of cosmology. They have a nice list of things which are mysterious. And this is never mentioned. To me, it's one of the biggest mysteries. Why is gravity so differently treated from everything else? Everything else was maximum entropy. Gravity was essentially minimal entropy. And it's a huge imbalance. Now, the scheme, which I'm going to talk about, if I can push the right picture. Now, this is actually just a picture showing you what this imbalance does. You see, when the initially uniform matter starts to clump, it makes galaxies and it makes stars. And it makes stars, and it made the sun, and the sun is what we rely on for life. Now, you might say, what do we get from the sun? Do we get energy from the sun? Well, then you might think, if the whole sky was the same temperature as the sun, that would be even better. But it wouldn't be any use to you at all, because it's not the energy that we get from the sun, it's the low entropy in the energy we get from the sun. Because the sun is out there, and it's hot, and you have a cold sky. The Earth doesn't get energy from the sun. if it did, it would simply get warmer, and after a few days, it would be completely intolerable. It would just, life would be impossible. But, of course, in the night, it all goes back again. But it all goes back again in low frequencies, and it comes in high frequencies. It's yellow light and infrared going back, basically. And it's this large number of photons going up which take the entropy away, and the low number which comes in a low entropy form. It's a point Schrödinger made a long time ago. But it's not very much appreciated, apparently. But the point is that it's the clumpiness of the material which enables stars to get produced, and black holes. I'm not going to explain the black hole so much. This is a space-time picture of a black hole, and the horizon is this little tube which comes up, and there's singularity in the middle. But the point I want to make is these cone things. What are these cone things? These are light cones, and you have to imagine that the space-time has all these cone things drawn on it, which tells you what light would do if it were there. You don't have to have light there, but if it were there, it would follow the cones. And I had a little bit of this with my twister picture. But what this represents, imagine a flash of light. The first picture is the flash of light in spatial terms with 3 dimensions, the spheres spreading out. But then I've got to throw away a dimension over here. So what looks like a sphere here looks like a circle here. And so the cone represents what light would do if it were there. And you have to imagine at every point in the space-time there is, in the tangent space, a little cone like that. Okay, which tells you most of the structure of the space-time. It doesn't tell you quite the whole structure because it doesn't tell you how clocks behave. It tells you, if you know about general relativity, you know that there's a thing called the metric, and the metric has 10 components, and 9 of them, or really the ratios of the 10 components, tell you where that cone is. So that's almost all the information. The one missing piece is the behavior of clocks. So you want to know how clocks behave, and this is a cartoon showing you different clocks, identical clocks, but moving with different speeds, and the first tick and the second tick of the clocks represented by these surfaces here. Okay. Now, the clocks, we have extraordinarily good clocks now, and the extraordinary precision of clocks depends basically, the reason that it's so good in a sense, the ultimate reason, is because of the 2 most famous formulae of 20th century physics. These are, well, one of them has to be Einstein's E equals mc squared. The other one is Max Planck's E equals h nu, or hf if you prefer f for frequency, but nu is my frequency. And if you put the 2 together, you can just eliminate the energy from them. See, Einstein tells you that energy and mass are basically equivalent. Max Planck tells you that energy and frequency are equivalent. So put the 2 together, it tells you that mass and frequency are equivalent. So if you have a stable particle, and this is the history of a stable particle, it is a clock of extraordinary precision. So this is indicating it's an oscillator. It has a very, very high frequency. You can't use that directly, but the good clocks that we have depend on this idea, not directly here, but basically the same sort of idea, is that you have this extraordinary precision because of the combination of these 2 very, very basic principles. So quantum mechanics gives you these very precise timing of clocks. Now, the converse of this, however, is that, let me go back to this first, that if you didn't have mass, suppose you just had photons, then they only travel along the cone. They're going zipping along here, and the first tick is never even registered. So a photon doesn't feel the passage of time at all. Now, why am I saying that? I can actually forget with my pictures what the next slide is, but I have the Escher picture. What's that doing? Yeah, I need that, I think. Let's come to this first, though. Imagine the very remote future. I should be giving you my universe picture, if you like. The very remote picture. And you wait for eternity. That's a long time. Well, you wait for, first of all, the Google years for all the black holes to go. That's the boring time when you wait for a black hole to evaporate away. That's really boring. But the very boring era was after that. There's nothing of any interest happening at all, as far as I can make out. And But I was sitting and worrying about this in my office. I think, isn't that a dreadful fate for the universe? Just interminable boredom. That's the fate of the universe. But then I thought, well, who's going to be bored by this universe? Well, not us, but it'll be photons mainly. And it's very hard to bore a photon. It's hard to bore a photon because, well, as Stuart will tell us, it probably doesn't have any experiences. But that's not the point. The point is that the photon zips along, doesn't even hit the first surface here. It doesn't even notice the passage of time at all. So it gets right out to infinity without noticing a thing. So that's the main point I want to make. And it's the sort of thing I used to play around with decades and decades ago, of squashing infinity down. And it was a good way of talking about radiation and black holes and the energy they carry away and that sort of thing, which is very topical now. But this is a very nice Escher illustration of a particular type of geometry. It's called hyperbolic geometry. Particular type of geometry where you can see infinity. So here these fish are supposed to be, as far as they're concerned, the same right out to the edge. So the geometry they use is such that their scale is, they sort of rescale the geometry so that they're the same right the way, as far as they're concerned, the universe is infinite, and even though they look to us as getting smaller towards the edge, as far as their geometry is concerned, they're the same size. And it's what's called a conformal squashing down, and you can see that particularly in the eyes of the fish because they're circles, and they remain circles right the way as close as the edge to the edge as you can get. So as far as these fish are concerned, they like the massive particles, if you like. This is infinity. The edge is infinity. But if they were like photons, they wouldn't care about the edge. And you can see that things which just respect the conformal geometry, that edge is just another place. So the photons go zipping off, and they could be right out there. So it's the same idea that's being used here now to talk about infinity of the universe. So what I'm going to do is to squash infinity down in the same kind of way. So what we have to imagine is that below this line, I'll tell you what that line is in a minute, but below that is somebody's universe. Let's say our universe. And this is its remote future. And as far as the photons are concerned, this is just another place like anywhere else. And so it comes zipping along, it says, well, where am I supposed to go after that? So that's after infinity. The idea is it goes somewhere else. Now, where does it go after infinity? Well, now let's think of us as the top part of the picture. Now, as you go back, this is supposed to be the Big Bang. Now, I talked about the Big Bang being a very, very special state. And I used to have some complicated way of saying that. But my colleague Paul Todd, who was a student of mine a long time ago, had a much better way of saying it. He says, just take the conformal geometry, which means just take the light currents, forget about the scale, and the Big Bang, the idea would be, is a nice smooth surface, which you could theoretically extend to before, but why bother? It's not supposed to be real, it's just a mathematical trick. So that was his idea. It's also physically a good idea, because you could say, well, it's not just photons, as it was pretty well here, but you've got all sorts of particles, but they're very, very hot and energetic, and the closer you get to the Big Bang, the more and more energetic they get, so they're behaving like photons. So they have effectively no mass because their energy of motion completely swamps their mass. And so they're behaving as though they had no mass. And so again, they say, well, why wasn't there an existence for me before the Big Bang? And that only works in these very special model, as I say, 10 to the 10 to the 124 special. These only very special models which seem to be what we seem to see is the universe like that. So the idea is that the universe was of such a character that you could extend it conformally to something behind. And then the crazy thought here, now all this isn't so bad, it's not totally crazy. The totally crazy idea is my idea here, which is to say, okay, this is drawn a little smaller, the picture I had of the Big Bang of the universe before, with its exponential expansion here. That's us, or we're down here somewhere. And you squash down infinity to make it a nice finite future boundary, like in the Escher picture. You stretch out the Big Bang, as Paul Todd suggests you do, And the crazy idea is that they match. Well, our Big Bang was the continuation of somebody else's remote future. Our remote future will be the Big Bang of somebody else. I call this our eon. That's the eon before ours. This is the eon that will come after ours. It's a little bit shades of the steady state model where one used to seem to have this continual universe. Well, it's philosophically like the old steady state model, but very different in detail. So this is supposed to have existed forever in this scheme. And there are various nice implications that the theory has, which are still being explored, and I think has a good chance of being right. There are the main observations. I don't think there's anything more on this picture, so yes, there's nothing more. So let me just say, there is the question is, could you imagine signals? Oh dear. I've done the press the wrong thing. Never mind. Could you get information through from one eon to the next? And the claim is, yes, you can. And I thought, what is the most violent process that I could think of which might get through? Well, I thought of collisions between supermassive black holes. Our galaxy has a black hole in its center, which is about the mass of 4 million suns, 4 million times the mass of the sun. We are on a collision course with the Andromeda galaxy, which has a much bigger one. I forget, I think 40 times as big. I can't remember the figure. But when we collide, which we will do in a few thousand million years, not that long, the black holes will maybe miss the first, they'll probably miss, but they may well feel each other out and eventually spiral into each other, and there will be one big whopping explosion, and that signal will go right out and will be detectable by people living in the eon beyond ours. So I'm saying that we could detect signals like that in the eon prior to ours. So it's a perfectly experimentally testable theory, and the question is it right or not? Well, I'll leave it at that point. Thank you very much. I'm afraid I probably went on far too long, but still.
Just fine.
Okay, thank you. Yeah. Oh, thank you. Yes. Okay. Thank you.
Thank you very much. Can anybody hear me in the back? In the front? Well, that was very nice, Sir Roger. That was quite thrilling to have you explain these concepts that have been so mystifying even to professional card-carrying physicists, and actually do it in person. And I was thinking, as you were talking about eternity, of Woody Allen's famous line that eternity is a very long time, especially towards the end.
That's right. Well, it's not so long for a photon, telling you that.
Right. Things are
Yes.
very laconic for photons. So, well, first I wanted to mention, I forgot to earlier tonight, that part of the reason that you're here is to sort of kick off this celebration and this initiation of a new center that we're forming here in La Jolla, called the Penrose Institute. One of the founding directors, James Tagg, is over there in the front row. And we're hoping to form a collaboration with the Clarke Center that will kind of spread the boundaries and increase the interactions, to use a physicist language, between the arts, the sciences, consciousness, the squishy sciences, the hard sciences, the life science. I always like when they say life sciences, because that means that physics must be a dead science. It's the opposite. So I wanted to take the opportunity to thank you for being a part of that, and we're looking forward to many more fruitful collaborations and interactions to come. I wanted to start off tonight with a couple of questions that I have, because I have the microphone. And then I thought it might be fun because you mentioned today over lunch or earlier in the day that one of your desires when you wrote The Emperor's New Mind, which deeply inspired me, was that you'd get mail and letters from young people that got inspired into the line of work that you practice. And you said you were a little bit dismayed that you got a lot of letters, but they were from mostly old men. And,
Yes,
and
true,
I saw
yeah,
some
right.
nice young people in the crowd, and I thought it'd be great to only take questions from young people tonight. How about that? But first, we'll take one from a reasonably old person, although I'm a cosmologist, so everyone seems young to me. So you mentioned, and I know that you actually had the fortune to study under Paul Dirac, and
Well, he was. I went to his lectures. Yes,
Yes, you
that's
attended
true.
his lectures.
Yeah.
His breaking of chalk inspired you to daydream and then kind of reconnect later on.
Yes.
But, here at the Arthur C. Clarke Center for Human Imagination, we like to explore the connections between the arts and sciences. And one event that we did last month or 2 months ago now was with Ray Armantrout, who's a professor of literature and poet and won the Pulitzer Prize in 2010. She's a member of the Clarke Center Advisory Board as well. And she and I had a great conversation, and we debated whether or not there's a relationship between science and the arts. And it's often, here we have classes, and I'm sure there are such classes as physics for poets.
Yes,
and I
sure,
debate,
yeah.
and she and I co-taught a class called Poetry for Physicists, and that was really fun to take that class and explore the commonality. But I remember mentioning in the first day of class that Dirac was famously anti-poetry, and he would even say things like, in science you attempt to explain the most complicated things with the simplest of languages, but with poetry it's the exact opposite.
Yes.
And I wonder, what are your musings? What similarities, differences do you see between these two different cultures as they've been described?
Well, it's undoubtedly true that aesthetic judgments are important in science. Well, I would say important particularly either in mathematics or in very basic science. You might have science, complicated things which might not be obviously beautiful. Well, biology, things are obviously very beautiful. But I don't know. Certainly, let's speak only for the fundamental basic sciences. Then it's undoubtedly true that there is a deep beauty in the theory when you get it right. But I think it's dangerous to argue the other way, because people often do argue, say, oh, my theory is so beautiful, it has to be true.
Dirac himself said that, right? That's
Yes, well, of course, he was rather more, had better luck than, I don't think we should call it luck, but he certainly had a fantastic reputation in getting it right. Although not quite always, but he had a very good, and certainly with the electron, there was some comment, wasn't it, that somebody asked him, when you were searching for the equation for the electron, how did you come across that beautiful equation of yours? He says, well, I have a very keen sense of the beautiful, and when I found my equation, I knew I was right. So something like that. Of course, it's probably totally apocryphal, that story.
Many stories about him.
That's right. But he did certainly value the beauty of the mathematics. Mm-hmm. I think it's undoubtedly true that if you get it right, I mean, the ideas of gauge theories, you see, it wasn't the idea, I mentioned the Kaluza-Klein model, but what really survived mainly was Hermann Weill's idea. He had a different way of thinking about how electromagnetism could be incorporated. And he had the idea, well, with Einstein's theory, you can have a vector and move it around a loop, and it points in a slightly different direction when you've moved it around the loop. But Weill's idea was if you have a little ruler, or the length of the vector, if you like, and you move that ruler around a loop, it might be a different scale when you get round. And he showed that the equations, Maxwell's equations, could be incorporated, Maxwell's electromagnetic equation incorporated in this idea. And then Einstein said, no, that doesn't work, because proton take it round a loop and it'll be different and it'll disagree with quantum mechanics and things like that. So Weil went away and said, oh dear, something, I don't know what he said. But then he and a number of other physicists came up with the idea, okay, when quantum mechanics became established, and you say, well, you've got this phase, and this phase is somehow an unobservable thing, and you can't really tell. It go around a loop, and it can get rotated round. And that was the phase idea, and that's what survives today. Mm-hmm. But of course, the name gauge theory, which was because originally it was a gauge in the sense of how big it was.
Railroad tracks.
And it's a bit of a misnomer now because it's not really a gauge in that sense. But gauge theory is the foundation of all of the physical interactions, I would say, except for gravity, which is a bit different. Well, some people say it's a gauge theory, but it's a different kind of theory. But the gauge theories of all the other interactions come from Hermann Weyl's beautiful idea. And fantastic.
So a lot of times, famous physicist Richard Feynman said, anybody who tells you they understand quantum mechanics is a liar. Sort of his polygraph test. What is it about quantum mechanics and cosmology to a certain degree as well that leads and lends itself to ribald speculation that kind of brings out, I'm sure you get your share of emails, and now you get emails instead of postal mail from people.
Strangely enough, it's usually relativity. I never understood that. You hardly ever get people complaining about quantum mechanics.
Right.
They complain about relativity all the time. Perhaps they don't understand it enough to complain about it, I'm not sure. But no, it's completely crazy. You see, I have to blame a lot of the crazy theories people have now on quantum mechanics, because it is a completely crazy theory, but it works so beautifully well. But see, there is this thing about not understanding quantum mechanics, and Niels Bohr has some statement of the same. I forgot what it was now. Yeah, if you think you understand quantum mechanics, you haven't understood it. But I forget now what the quote is.
Same spirit, right?
Same spirit. This is fine. But you see, there are two reasons, and I think there are two quite different reasons. And in one of my books, I said there are two different kinds of mysteries. They're the X mysteries and the Z mysteries, or the Z mysteries, if you prefer that. The X mysteries, well, the Z mysteries are the ones that you can sleep peacefully with. That's the Zs, you see, of snoring or something. They're the puzzle mysteries. They are puzzles. And for example, the entanglements, which are very mysterious things. You get particles can be very far separated, and they still share information in a certain sense between them, which cannot be explained in a classical way. So it's purely quantum mechanical, these entanglements. And you can do experiments on this, which seem to influence what the experiment does over there, but not in the way that you can send a signal. Very strange. And that's a puzzle mystery. It's not inconsistent, it's just extremely puzzling. But then there are the X mysteries, and those are the ones that should be crossed off, in a sense, you see. The paradox mysteries, so that's the X and paradox. And Schrödinger's cat is a paradox because it doesn't obey the Schrödinger equation. And you see the cat is either dead or alive, or it's gone through one door or the other door. It's not in a superposition. And so it's really a paradox with what we see that the world does. Well, people have their ways of resolving it. And either you have to go into many worlds, and then you have to go into the many. It doesn't make sense in my view. You've got to explain the world we actually see, not a whole host of things we don't see.
Yeah.
And that's one thing which doesn't explain it. Another thing which doesn't explain it, which is the conventional quantum mechanical view, is that somehow the system gets entanglement with the environment. And then you say, well, you don't know what the environment's doing, so you do a trick which is sort of tracing over it. But it doesn't make sense if you look at it. It's what I call a double ontology shift. You have one ontological view. You say, well, the wave function describes the world, if you like. And then you say you've got to average over these different things. And then you use another descriptor, which is called density matrix. And that allows you to do this averaging. So you shift from the wave function, or the state vector, to the density matrix. And then you do a little rotation of the density matrix, which is perfectly legitimate within the world of density matrices. And then you say you've diagonalized it. You say these numbers down the diagonal represent probabilities. And then you say, well, it's a probability of different states. Well, that probability of different states is shifting back to the original ontology. And you've gone through and then back again. It's a complete cheat. Right. You haven't got a consistent way of representing the world.
Continuously, so. Right.
So you have to make a jump and then a jump back. So it doesn't really work. So you've got to do something new. That's not quite fair on. There are models. I mean, there are other models in the world I sort of hinted at here, certainly which preceded the one I was talking about. There's the de Broglie-Bohm scheme, One trouble with that, it's rather a mess, that's one trouble. But one trouble with it is it doesn't claim to have different results from quantum mechanics. It just has a better ontology. I think it does have a better ontology, but it doesn't really do anything for you. These other schemes by Girardi and his collaborators, which were much better in a sense, that they were deviations from quantum mechanics which could in principle be detected, which a class of theory some were disproved. But I mean, this is serious science. You can see, is that theory or is pure quantum mechanics still true? Do you have deviations from standard quantum mechanics? So the reason it doesn't make sense is it's not a consistent theory.
We're trying to put it into a box that we can comprehend, but it doesn't mean it's
so it's not our fault, it's the fault of the theory we have. Yes.
So I think I turned this up. So having touched upon deep space, cosmology, rocket science, I thought we'd turn to something simple like brain surgery and neuroscience. So like many of the audience members, I'm guessing you arrived here tonight trusting your life, essentially, to software, to a computer that you probably have in your pocket or your car has on its dashboard, a computer that guided you, and you basically trusted it completely with your life, and certainly with being on time here tonight. I usually turn off the actual voice commands when I'm driving with my wife, so I don't have two women yelling at me. But I wonder, as computers get more powerful, as we're already building the fundamental qubits in my laboratory and here at UCSD and other groups around the world for quantum computers. And I wonder, we hear about this logical progression where, chess is very hard. And humans are very good at chess, and then humans were beaten by computers at chess. Therefore, computers are going to take over the world, and software someday, especially even in the absence of advanced hardware, which we're developing here at UCSD, at Cal IT2, and other places. How is it in your mind? I mean, do you really envision that the ultimate evolution of quantum mechanics will be to describe quantum computers as brains, or vice versa, or similar in a Turing sense that could not be distinguished?
Well, you see, the view I have is actually not. You see, people complain and they say, well, you're saying consciousness is a quantum process and the brain is warm and messy, and how do you get quantum mechanics? Well, you see, I'm saying something worse than that. I'm saying it's not just quantum mechanics, it's where quantum mechanics goes wrong. See, so we don't even know it goes wrong in this way because of experiments which have not yet achieved that level. So I'm hoping that they will show that it goes wrong in the way that it's claimed, because the scheme that Stuart and I have developed in various ways depends on that scheme. So I think there's good reason to believe that it does go wrong at that level, but we need better than reason to believe. We need experimental evidence that that's correct. But this is, as I say, going beyond a quantum computer idea. It's saying a beyond quantum computer. So it's more exotic. Now, you see, my position is that quantum... See, there's different things here. I'm saying that consciousness is something which is not a computer action. It's not the inaction of an algorithm. It's something beyond an algorithm, which enables you to achieve things which pure algorithms don't achieve. And we know that there are, mathematically, we know there are limitations. That's absolutely established mathematics. And these limitations are well understood. But whether the brain does something different is another question. And I believe that you can make good arguments that it does do something different from pure computation. And if it's a quantum computer, it doesn't do that. You see, quantum computers just do computation. They may do it faster. There are certain types of computation that they should do faster. It's a little bit limited at the moment, what they seem to be able to do. It's not really like an ordinary computer where you can program it in all sorts of different ways and it does fantastic different kinds of things. Whereas a quantum computer, it's just a very limited number of things that we know it can do in principle better than an ordinary computer. But maybe that's a temporary stage. But it's still only doing computations faster, or more bigger computations or something more powerful. So there's not a qualitative difference in what they can do. the claim is that if you could have a beyond quantum computer, I think there's a name that people have given to that, that incorporated whatever it does, whatever the world does when it reduces the state, and that's what Stuart and my ideas suggest would have to be the case. Yeah, that would be, it could. But you see, it's not on the spectrum of what can be achieved. You see, people talk about 10 years, 20 years, even 30 or 40 years, but this is something which we have no idea how you would do at the present time. Yeah.
Very good. So I'd like to take maybe 2 questions from audience members under the age of 7. No, I'm just kidding. Maybe preferably a young man and a young lady could ask a question. That would be fantastic. Is there a volunteer in the back? Young man? Young man, okay. Let me see, none of my students qualify as young. Okay, well, we should start with the youngest possible. Are there any questions up in the front? I see some very angelic young faces here. Here's one, okay. Is your chance to interact with physics royalty.
Hi. Thank you for speaking today. This has been really interesting. But I had a question about your cosmological theory concerning the aeons and the inevitable Big Bangs. So if I understand correctly, what you're saying is that in our distant future, there's going to be a Big Bang, and then in that universe's distant future, there will be one. But if the rarity of a Big Bang exists, then are you saying that it's a rarity that is inevitable, or that the first Big Bang was just a very rare occurrence, and that now it will no longer be a rare occurrence?
I didn't quite catch the question. Sorry. I can tell you that I'm not sure whether I caught exactly what the question was. I'm sorry.
Oh, sorry.
Yes.
Was there a first Big Bang?
Oh, first Big Bang. When the scheme I have, they go on indefinitely. So there wasn't a first one. It's a bit like the steady state model in that sense, that the universe was already there. I worried about this because I once gave a talk in the Vatican, and I was worried that this model would not be viewed with favor because the origin of the universe was supposed to have been at a certain stage. But they took what I regard as the correct attitude from their perspective, namely that the creation of the universe was the creation of the entire thing, all there, boom. And so, not bang, but boom, I suppose. This whole thing was this infinite sequence of things. Yes, but it doesn't have to be like that. It could be something where there was really a beginning one. And so how would one tell that? I have no idea. You need a good theory which really pins it down much more than I'm able to at the moment. So if the theory really demands that it does go on forever, and that would be the way I view it, then that would be it. Yes, there is no original one. It was there forever.
Okay, great. Maybe one more question. Oh, there's a very young man in the front. This will be our final question, and then we will take the break, and there'll be some book signing out in the room next door. Let me make sure this is on. Here you go. He's already got a copy.
Thank you. So my question on consciousness is that in thinking about data and what we see and what we can test and demonstrate on consciousness, when we see, for example, not religious near-death experiences, but they die on the table, they go to another room, they report things sometimes miles away. In theory, what would you say could explain this?
You're thinking about sort of ESP, you mean?
Yes.
Yes. Well, I'm not a fan of that idea, partly because, well, you see, I mean, who knows? But I suppose the idea is some sort of quantum entanglement between states, between brains in different rooms. I don't know how you'd get that from one to the other. That's the problem. I mean, it's hard enough in a single brain to see how you can get the kind of entangled states that you need for this scheme. You certainly need something which would cover large areas of the brain, so that the quantum state, if you like, isn't just within a single neuron. It would have to be extending across several, maybe loads and loads of neurons altogether. So there is some kind of, not exactly EPR, but that extrasensory perception is that extrasensory, what's the R stand for? Anyway, the thing is it's within one brain, but if it's from one brain to another, I really have no idea how you could conceivably get the entanglement established. It's hard enough in a single brain to see how that's going to work. So I think it's a pretty long shot.
Thank you.
I'm afraid.
So part of the reason I wanted young people only is so that I can get first dibs on their applications to come to UCSD. Thank you, young people, for your questions. I'm sure there's many more. We'd like to thank Sir Roger Penrose for coming tonight. Thank the Penrose Institute. Stuart Hammeroff. We have our conference on consciousness going on at the Hyatt Aventine. I believe there might be some tickets still available for that conference. And thank you so much for coming on behalf of the Arthur C. Clarke Center for Human Imagination. We should be televising this event in a couple of weeks. Within a couple of weeks, you'll be able to relive it again in a future universe. Thank you very much.
Thank you.